Again, the first one we will talk about is the uniform distribution. Here, the PDF is flat, and the sample space is the interval from A to B. Obviously, the length of the interval is B minus A. Therefore, the PDF here, well, here we are not talking it with PMFs anymore. We are using PDF. And the PDF is given by 1 over B minus A, so that the area under it is equal to 1. And of course, by integrating this, you can obtain the CDF as given here. It's 0 below A, and it's x minus A over B minus A linear function from A to B. It starts from 0, and it goes to 1 at B, and it stays at B at 1. So it's something like this. Okay, this is the CDF. And you can compute the expected value and the second moment and the variance by these simple integrations. I'm not going to do them. I'll just give you the results. This is as expected. Again, the midpoint, the expected value. And this is the second moment. And of course, when you subtract the square of the first moment from the second moment, you get the variance, which is given by b minus a squared divided by 12. So the next one we will talk about is the exponential distribution. Again, the parameter used for the exponential distribution is lambda. Later on, I'm going to give another parameterization, but for the time being, and actually throughout this course, we will use this parameterization. The PDF is given by lambda times e to the power minus lambda times x. Okay, and this is a one-sided distribution, and is defined for x greater than or equal to 0, and it's something like this. Something like this. Okay, this is the PDF. Starts at lambda. It takes its maximum value at lambda, and it's a convex curve. And if you integrate this, you get the CDF as, well, beyond 0, you get 1 minus e to the power minus lambda x. And by evaluating this integral, observe that it starts from 0 because, well, the support is from 0 to infinity. You get the expected value from this integral as 1 over lambda. So this is typical. If the PDF of the expected value is given in this form, the expected value turns out to be 1 over lambda. And it's not also, again, difficult to compute the second moment. I'm not going to give out the details, but using integration by parts, you can compute this integral, or you can have it computed by a computer, and that turns out to be 2 over lambda square. So from 2 over lambda square, which is the second moment, subtract the square of this 1 over lambda, you get 1 over lambda square, which is the variance of the exponential distribution. And finally, here I give the characteristic function of the exponential distribution, computed by this integral from 0 to infinity. Starts from 0 because, well, this is the distribution is non-zero only in this interval. E to the power j omega x times, this is the PDF. Integrate this. Again, you have an exponential term here, so you can merge these two. I'm not going to do it, but this is a very, very simple integral, and the result is lambda over lambda minus j omega. And here you have the Laplace transform of the PDF. Similar to the generating function in the discrete case, Laplace transform of the PDF is defined for random variables where you have a one-sided support from 0 to infinity. So the integral starts from 0. And this is the definition. This is the expected value of e to the power minus s times the random variable x. And again, this is, you have two exponential terms, quite easy to integrate. And this evaluates to lambda divided by lambda plus s.